Well, hello. It's nice to see me again. I can't see you. I wish I could. Maybe one day we'll be able to do this in more of a live setting. But I hope you are well. I hope you are staying away from other people. Anyway, I miss you guys. I miss the fun we have in class. Shoot me a text now and then if you get real bored. It's kind of nice to hear from you and remember that we still are connected, even if it's a little bit more distant. So today we start into a brand new topic, and hey, it's not triangles anymore. We're definitely going to work on circles for the foreseeable future. So circles are fun, and what I'd like you to do to start out with is, to the best of your ability, draw a circle. So if you don't have paper handy, you might want to go get it. You can pause this recording anytime you want. But let's make circles here and see what we can figure out about these circles. So, erase this. Let's talk about what's important in a circle. First of all, every circle has to have a center. Go ahead and take a second and put a center into your circle. And then we also know that circles are, circles are split in half by diameters. So I'm just going to point this out as a diameter. And that goes the entire length across. But then, of course, we have this other thing we can draw, which is only halfway across, which we call radius. So we'll label this as a radius. So just some very basic definitions and characteristics of a circle. What I want to focus on right here, though, is the idea that when you have two radii drawn, it actually creates an angle in here. And we're going to use a notation now that I kind of slipped up and used a couple times earlier in the year. Haven't really formalized it, but I'm going to use a Greek letter. It's the Greek letter theta. So let me explain what this is. It's like a number 0 with a line through it. It's the Greek letter theta, and it represents angles. So like we typically would use like x and y for unknown sides or unknown values. In geometry, we use theta to represent some unknown angle. So this actually has a special name to it, though. We call it a central angle. And that may not make a lot of sense until we get a little further into this when we talk about something else called an inscribed angle. But for now, the central angle is an angle formed at the center of the circle by two radii. And you can kind of ignore this part over here of the diameter. It's two radii. Okay, good. So now here's what we have. I'm going to label some of these points here. We have a center here, C. We have a point, we'll call this A here, and a point B there. And anytime you have a central angle of a circle, it's going to intercept a part of the circle, that part right there, which we call an arc. It's a C, arc. So an arc is a portion of what is effectively the circumference of the circle. We're going to use that to our advantage here in just a few minutes. And one fun little note here is that the measure of the central angle, how do I say this? The central angle equals the arc measure. So this can be a little bit confusing. I just want to mention it now so we get over it. There's two things we're going to deal with. One is arc measure, and the other one is going to be arc length. Let me just clarify this real quick. The arc measure is measured in degrees. And there's 360 degrees of an arc. So if I go all the way around the circle, that would equate to an arc of 360 degrees. An arc length, which we will talk in detail about in about 5 minutes, is the physical length of this line right here. Like if you laid a piece of string around this line right here, how long would that string be? So you measure arc length in, like, you know, centimeters, inches, feet, that kind of thing. But you measure arc measures in degrees. And so the measure of the central angle in degrees will always equal the arc measure in degrees. 90-degree central angle, 90-degree arc measure, and so on. Okay. But it turns out that there is another way to talk about getting from A to B around this circle. So certainly I could move from A to B the short way, but what if I had a point D over here and I went this way, all the way around from A to B? That's another arc, actually, but it's a really big arc. And so that leads to two different distinctions we can make for arcs. One is a minor arc, which is less than 180 degrees. And one is a major arc, which is greater than 180 degrees. So for a minor arc, we would label this one over here as A, B, little arc symbol over the top, like that. So anytime you just have 2 points and you label them with the two coordinates, you're talking about the shortest path from A to B, which has to be a minor arc. If I wanted to go the other direction and make it a major arc, I'd have to include this point D. I'd write it as A, DB, and I'd write that arc, and that tells me, okay, I'm going to go from A through D all the way around to B. Okay? I would ask for questions here, but of course you can't ask questions. By the way, if you do have questions, you can always pause the recording, write down your question, and then shoot me a text or send me an email or something, and then you can keep going again. I won't obviously be able to answer it in real time, but it won't be too bad. So like another circle here, you might want to make one too, just because we're going to do a lot of this today. But my center here, I'm going to draw a straight line a couple times. I'm going to create this angle theta. And I'm curious about, we're going to call it S right here. I'm curious about this length right here, of how we would find that length. And of course, when I say I'm curious, I mean I'm going to teach you how to do it. But that's a little tricky, because like it's, I don't know, it's a part of the circle, but how much of the circle is it really? Then I think to myself, wait a minute, S is sort of related to the whole circumference of the circle. Remember circumference? C equals 2 pi r. And theta is associated with, well, it's connected to the 360 degrees in the circle. So what if I set up this relationship? Bear with me here. What if I look at the ratio of theta over 360? Like if theta was 90 degrees, then I'd have a fourth of the circle. 90 over 360 equals 1/4. If theta equals, I don't know, 10 degrees, I'd have 1 over 36, 10 over 360. So I'd have, this is some portion of the entire 360 degrees in the circle. And I think that that fraction right there is the same as S, this little bit of the circle arc, over the entire circumference, 2 pi r. So now what I think I could do is I could use a little bit of algebra here to solve for S. Luckily, we're really good at that now, right? We multiply this side by 2 pi r, multiply this side by 2 pi r, so those cancel. And S equals theta times 2 pi r all over 360. And I'm going to show you something on a different screen now that I hope will maybe make some sense. So I should be sharing this with you. This is kind of like what you have. By the way, I'd like you to make sure you have this handy. We're going to use this pretty quickly, and we'll use this intermittently throughout the next couple of weeks. But so I just want you to look at this drawing real quick. We have a angle in the middle, or central angle theta, with some arc length, and theta is theta over 360 of the circle. And we know that this arc length is the same proportion or same portion of the circumference, which is 2 pi r. So here you see the same, can I do this? Maybe I do this. Right here, you see the same expression that I showed you on the whiteboard. We'll go back in just a second. Another way to look at it is this sort of proportion we have right here. And it's using different letters, A here instead of theta, and L instead of S, but it's the same concept, that whatever proportion or whatever portion of the 360 degrees we have in our angle, we also have as part of our circumference. So if I go back now to the whiteboard, you should see why that makes sense. And so now you can calculate the length of any arc based on only knowing the central angle, and of course, knowing what the radius is of the circle, so you can find the circumference. Okay? All right, let's move on to something else. The next piece of this might be a little bit mind-blowing. Anyway, let me just go through it. We know all about degrees, right? We can measure things in degrees. We've done that a whole lot. We know there's 360 degrees in a circle. We certainly know there's 180 degrees in a triangle, and then we've done the other polygons as well. But it turns out as you start getting into working with circles in a little more detail, there's another unit that is commonly used to measure angles. And it's called a radian. And you might remember when we were doing those trig problems the last couple of weeks, and I had checked your calculator to make sure you're in DEG mode instead of RAD mode. That's what this is. So let me show you a little bit about what a radian is, and I think it's actually kind of cool, but maybe you will prove to me otherwise. So let me put theta in here. And so here's the thing I want to do. I want to try to imagine what angle I would have to have in order for, watch this now, this length right here, the length of this arc, to equal the radius. I think I'm close there, but can you look at that and see, does the length of that radius here match more or less the length of the arc right there? Where that happens, we define as being 1 radian. And I don't think it's a coincidence that radian and radius sound alike. So there's 1 radian that creates this arc that has an arc length that equals the radius. But here's what gets really tricky now, okay? Watch this. A circumference of a circle is 2 pi times r, right? So pi is 3.14, right? Hey, happy Pi Day. It's 3.14, so 2 of those is about 6.28. There's that many r's that go around the circle. So if this is 1 r, maybe another r might be there, maybe another r might be there, and so on. And we're saying that there's about 6.28 of these, or 2 pi of those, as you go around the circle. Well, if theta is the angle that makes 1 r and is therefore 1 radian, then where we have 360 degrees in a circle, there are exactly 2 pi of those in a circle. That's mind-blowing, isn't it? Let me back up and tell you, say this again, see if I can try to make more sense. I've created an arc that is exactly the length of a radius, and I know there's 2 pi of those as I go around the circle, a little over 6. So like 6 will get to me right here, and then there's a little bit more on the end. So there's 2 pi of these to go around the whole circle. That means there's 2 pi of these to go around the whole circle, but this is just 1 radian. So if there's 2 pi of those, there's literally 2 pi radians that go around the circle. And this relationship right here is a fundamental relationship of what you'll do when you get to trigonometry. And those of you know that folks that are in pre-calculus are certainly doing this right now. So this is kind of a new thing. We know 360 degrees, but we're now aware of this reality that if we measure angles in radians instead of degrees, that there's 2 pi of those as you go around the circle. I know, kind of mind-blowing, but still pretty cool stuff. Okay, the third big topic of today is going to involve another circle, but more importantly, it involves, let me go back here, to pizza. Hey, pizza. So it's great to talk about the arc length, but I mean, frankly, in a pizza, that means crust, and crust is ew. No, it's not ew, it's fine, but I mean, pizza is pizza. Pizza's delicious. So what would it look like to have not just a piece of the crust, but all this yummy, delicious pizza? How would I figure out how much pizza I get for a given problem? So I'm going to give you a little bit of a problem, and let's figure this out. I want to know how much pizza I'm getting. Well, obviously, there's a lot of stuff I need to know. I need to know the radius for sure, because I know that the area of a circle is pi r squared. Do we know that? You ready for the joke? Well, if you say pi r squared, pi aren't squared. Pi are round. They're not squared, they're round. Okay, look, okay, whatever. So I need to know the area of the entire pizza, which is based on r, but I also need to know what portion of the entire circle I have. So I have to know this angle theta again. And it shouldn't surprise you to find that we're going to have a very similar type relationship here. I know that if I have theta out of 360, that's going to correspond to, we'll just call this A for area. My area out of this right here, pi r squared. I think I have something to show you here. Let me go back to this real quick. So this is the setup we have for finding the area, not the circumference. That's the crust. This is, well, the nasty part of the crust. This is saying that if I have an angle x, and by the way, that angle would be right here. So x would go right there. Let me make this fancy here. Oh, apparently I'm not going to be able to do that. If I have a certain angle there, then it is the same proportion of the circle as my area is of the entire area of the pizza. So what does that turn into? It turns into area equals theta times pi r squared over 360. Let's just figure this out real quickly. Let's say we go down to the bakery and we get, oh, bakery folks, I'm so sorry. I assume that there's got to be a 16-inch pizza down there. And 16 inches, by the way, means in pizza lingo, means the diameter. So 16 inches, that's diameter. So radius is 8 inches. Okay? And we'll just say that they're being generous. They cut the pizza into 8 pieces. Great. You want one piece. How much do you get? So let's figure this out. We know that the area of a circle of the pizza here is going to be pi times the radius squared, which is 64 pi square inches. I know they're not square, I know it's round, but that's how we measure area, is in square inches. So I can put that here as my area, 64 pi. Remember, I want to solve for this, the area of my pizza, of my slice. If there's 8 pieces, that means I've got to cut 360 degrees into 8 equal angles. Remember how that works out? 360 divided by 8 is 180, divided by 4 is 90, divided by 2, 45 degrees. So I can take this right here and write 45 degrees. But here's a little secret. If I know that I cut the pizza into 8 pieces and I'm just going to eat one of them, I could just replace that whole thing with my one piece out of the 8 total. I could do that. Let me show you now what happens when I do that. When I multiply both sides by 64 pi, and this cancels, I get a pretty big number here. I get 45 times 64 pi over 360. Okay, if you want to use a calculator, you can use a calculator, but I want to be a little bit smarter than that. I want to believe that I can take this ratio right here and make it look like 1 over 8. But to be clear, it doesn't happen every time like that. But I think I can cancel that to 1/8. And then I get 64, cancel that 8, I get 8 pi. So I can write it as 8 pi square inches, or I could use my trusty calculator, which is right here. 8 pi is 25.13 square inches. And if you're sitting there thinking, hey man, couldn't I just take that and divide by 8? Yeah, I absolutely could have. That would lead you down to the 8 pi. But let's keep in mind, not every pizza is cut into 8 pieces. Not every sector problem, a sector is considered this right here. Not every sector problem is a pizza problem, and not every angle is going to be exactly 1/8 of the circle or 45 degrees. So let me give you a new problem here just to show you what this would look like if it wasn't quite so obvious. So here's our center. Oops. Here's our center. Well, I'm going to draw there, and I'll go like here. And I'll say that the radius is 5. We won't even put units in here. And the angle theta is 115 degrees. And I want to find what the area of all that is. So now obviously it's a little bit more tricky. So let's go through this. 115 over 360. Remember, you have your sheet of notes here that tells you exactly how to set this up. 115 over 360 equals area, put whatever letter you want in there, over pi times r squared. So this is going to be 25 pi. So I hope you can see I can multiply both sides by 25 pi, and the area is going to equal 115 times 25 pi over 360. Hey, well, what do? I go 115 times 25, and I get 2875. And then the pi. So you're going to have pi in a lot of your answers here, but what do you do with 2875 over 360? If I divide by 360, I get some funky, weird fraction that I don't want to deal with. So the best I can do is start dividing this and reducing this as far as I can. And I would reduce it maybe by 5. So 2875 divided by 5 leaves me at, and 360 divided by 5 is 72. So maybe that's as far as I can go. If I'm asked for an exact answer, I would give that answer. If I'm asked for an approximate answer, then I just write this out and I get 25.9. And that would be, that seems awfully low, but that's it, 25.09. So what have we done? We found the length of an arc as a portion of an entire circumference. We've found the area of a sector as a portion of an entire area of a circle. And we discovered this thing called a radian, which is a new way for us to describe angles just using a different measurement tool, 2 pi radians in one circle. So here's the plan. When this is done, you're going to have a couple days to work. It looks like you've got 2 assignments that will be available, one from the book and then one on my handout. I also will try to take these slides, there's 5 slides here that I wrote up, and obviously out of context they might not mean anything, but if you watch this recording a little bit, maybe you can have those to look at as well. So I'll upload those as well, and then you have those to work from. So have a great couple of days. I'll see you again on Wednesday. And yeah, keep in touch. I'll be calling you, by the way. Each of you will get a phone call from me this week, so you can look forward to that. But I just want to check in, make sure you're doing okay, and then also see if you have any questions about what we're doing. All right, stay well. See you next time.